many familiar faces and also so many new faces. Yeah, so it's like, for me, I really feel like, because I have been here for 5 years, so I really feel like today I just came back to my parents' house and I just couldn't wait to share all with my all family member that what I have experienced over the last few years. So to be honest, for this talk today, it really took me a long time to figure out like what I should talk about today, because I had worked with Steve for more than 9 years, and even after I left UT Southwestern, I still try to follow like his vision, his research studies, and try to adapt his method into my own studies. So I figured out that maybe it's not a good idea if I just talking about the technical part today, because it will be so familiar to what Steve and Xun has done over recent years. So I think maybe I can share some of my personal experience and the lessons I have learned from like the development of a few R1 proposals. So I think that may be a little bit helpful to share today. So that's why I have this, according to David, this funny title today. So over the last 3 years, when I was at Emory, I had this like 3 ongoing projects, and I also like write 3 proposals. So because of the time, maybe I will just focus more on the first 2 and spend a few minutes on the third one. So the first one is about AI-driven automatic treatment planning of stereotach reduced surgery for the management of multiple brain mets. So here is the story why I started this project. So when I joined Emory in 2019, I was assigned to cover the main campus and also a satellite. So it's like 2 days per week for each site. And at that moment, the satellite was really very short-staffed. So it only have like 3.5 phases, including myself, to cover 2 Linux and Gamma Knife and a super busy HDR program over there. So at that time, like every phase, it just act like a firefighter. So we need to kind of cover for each other whenever needed and to do whatever I was asked to do. So although my major duty was doing brachytherapy and also do like a Ph.D. stuff, but I still need to cover Gamma Knife for a little bit, although I'm not trained for Gamma Knife. So I need to like help with like importing images, printing plans, monitor patient, and also sometimes doing the Gamma Knife treatment planning. And at that time, that was in 2019. So that was before the new version of that Lightning TPS for Gamma Knife. So at that time, we still use forward planning for Gamma Knife at Emory. And so forward planning is that the planner needs to manually place the radiation shot one by one and adjust the locations, the size, the shape, and the relative weight, repeatedly until get a good plan. So like as shown here for like a Gamma Knife shot, it is composed of like 8 independent sections, and each section can have 3 available collimation size, and it can also be closed. So in total, like we can have more than 60,000 available different shot shapes. And also technically, any location within the target should be considered as a candidate location. So that means there's a huge degree of freedom involved in Gamma Knife treatment planning. And I have found that this treatment Gamma Knife planning is the most challenging work I have ever had. And also the resulting plan quality heavily depends on the planner's skills, experience, and the available time they can devote it for to develop this plan. So here I show an example of the progress of the forward planning. So for example, for here, the red line is the target contour, and we try to place like the Gamma Knife shots to cover this target. So you see the planner first placed the first shot using like 8 collimation and 16 collimation, this composite shot. But you can see like still lots of parts of the target are not covered. And also there are a large portion of those coming to the nearby brainstem. So the planner decided to rotate the first shot by 90 degrees so that he can reduce the dose to the brainstem, and then he started to play the second one, the second shot, and adjust the location, size, shape, and the relative weight. And he may also need to go back to the first shot to do the adjustment. And then keep going, he plays the third one. And the final plan end up with 11 shots. So you can see it's a very like a trial and error process. And actually at that time, the commercial system called the LGP system, they already have that in inverse planning module. But I just talked with our physicists and physician, like why we still want to have this forward planning. They said because at that time, the inverse planning didn't work very well. So that's why I start to have this idea, like maybe I can do something there, try to improve the Gamma planning just to ease my own life. And then at that moment, I think Steve and Dan and Xun, they got their new R1 about this AI-based treatment planning for LINAC-based radiotherapy. So inspired by their grant, I'm thinking, okay, maybe I can steal their idea and use for my own application. So that's how the story starts. But then because this is a very like a proposal-oriented project. Because at the beginning, I already make mind that I will submit some proposal. So then I start to have some concerns like, is there enough significance for this project? Because the gamma knife radiotherapy is a much smaller field compared to the LINAC-based radiotherapy. So that's my first concern. And then second, I'm thinking, is there still enough innovation? Because Steve, they already got this AI-based auto planning. Should I still doing this? So I have lots of connotation. And the third concern is that because actually at that moment, I didn't have lots of experience about the gamma knife, either clinical-wise or research-wise. So I'm not sure whether there are already some very similar gamma knife-related project being funded, because I don't want to waste my time. So what I did is try to answer all these questions by using this NIH reporter website. So I have found this is a very useful tool for me to develop ideas and develop the proposals. So right now I use this website as much often as I use Google Scholar. So I try different like keywords combinations just to search all the related proposal, the funded grants, and like read through all the abstract one by one. So finally I found, okay, at that time, there were about like 9 or maybe more like very related funded R1 projects. So with this, at least I was convinced that doing radiosurgery related research can have enough significance for R1 proposal. So my first concern got addressed. And then I found this grant, which sounds to be very, very similar to what I want to do. And it turned out to be Dr. Xuejun Gu and Dr. Lu and Dr. Wadek's R1 grant. So actually, we got this grant when I was still at UT Southwestern. So I knew it was about gamma knife, but I didn't know too much about that. So I just read carefully about I read their abstract very carefully. It's just like doing the English reading test. So I read the abstract a few times and I try to summarize what they try to propose. And then I try to write down all their highlights of that grant. So I figure out that, okay, because they are trying to propose a new treatment strategy that is a special temporal distribution, and they are going to do a clinical trial about that. And although they also propose to do AI-based like plan optimization, but I figure out like their main priority will be just how to use the AI to automatically determine the optimal like shot scheduling for this spatial temporal distribution. So I think it's still very different from what I want to do, because my idea is still for the conventional gamma knife treatment, and also I will focus on how to automate the treatment planning in order to improve the quality and the planning efficiency, and try to reduce the quality variations among cases, among planners, and among institutions. So I think, okay, there may be enough difference between their funded grant and my idea. So I persuaded myself to keep going. Yeah, so I started this journey of developing this project and developing this proposal. It almost took me like 3 years to do this. Because I found that the commercial system didn't provide us a very good interface for me to do research. So as the first step, I have to build everything outside. So it took me about like 1 year to build our own gamma knife dose engine, and then develop our own like inverse planning module that I can use externally, independently. And luckily, I got that paper published about like our own inverse planning for gamma knife. So that became one of very important preliminary results for my proposal. Then the second step will be with my own inverse planning module. Then how can I automate this inverse planning? At that time, actually, I didn't have any experience with deep learning, because when I was doing the residency and still they started to doing research about AI, so I just missed that. I have no experience at all at that time. And then I just did a lot of literature review. So you see here, that's the biggest difference from my previous research. Before, it's more like method oriented. I will focus is like try to develop a new method, but now it's all opposite. My priority was totally shift. Like my first priority was just try to find, I think, a critical clinical problem. Then I can either develop a method or try to borrow or steal some method from Steve to solve my own project. So that's very different. And then I did a little review. I think about, okay, if I want to use AI to automate the treatment planning for gamma knife, I have like major two choice. One is to do the dose prediction using deep learning, and another is try to automate the priority tuning. So at that time, I actually already determined that I will select this brain mets as my disease type for this proposal. This decision was made first is based on the patient population, and also based on the challenge, because it is very challenge for automatic planning for patient with multiple brain mets, because there's a large variation in the number of brain mets, and also large variation in the location of the mets. And because of the very variation in the location of mets, then we also have a large variation in the relative spatial relationship between the brain mets to OERs. So because of these large geometry variations among brain mets patients, then I'm thinking maybe that those prediction may be not a good option for this project. So I decided to go with this automatic priority tuning using Xun and Chen Yang's method. So I started my preliminary study, but at that time, or even now, I still don't have very clear picture that how should I deal with this large geometry variation. I even discussed with Dan today, like how can I address this problem. So, but I still want to start the preliminary result study and get the result as soon as possible to submit a proposal. So at that time, I just decided I will go with a much easier type tumor type instead of brain mets to start. So I select this vestibular schwannoma as my starting point. So the reason I select this disease type is because first, they only involve a single target, and also with very relatively fixed tumor location. So then it will become more like a prostate cancer or pancreas cancer. So I know like what OERs I'm dealing with for this type of disease. And another reason is that the Western schwannoma is still considered to be very challenging for gamma knife planning, because you can see that the target is very irregular shaped. That's very difficult for gamma knife planning. And also it's pretty close to brainstem and cochlear. So our physicians still think this is one of the most challenging disease type for gamma knife planning. So that's why I target this vestibular schwannoma as my target for the preliminary study. So then I called Xun. I had multiple discussions with Chen Yang, and I used their method for my own project. Actually, I didn't do many improvement on their method. I just tried to adapt their method for my own application, and I designed my own scoring function based on our own institutional planning evaluation criteria. Yeah, so there's no much a technical part I can talk about that because I steal others' methods. I just choose five patient cases with very different geometry, and train this AI planner network. And I use 16 new patients as my testing cases. So I actually got a pretty good result, so we can publish another paper as a strong evidence for my proposal. So you can see that the average score that we obtained for the plan by the AI planner, the score is even a little bit higher than the plan that achieved by a very experienced gamma knife planner by manual priority tuning. And I also show the process of this automatic tuning process. So you can see at the beginning with the initial priority, the cochlear dose is pretty high because our criteria is 4 gray, then it's 9 gray already, and the total beam on time is pretty long. So you can see during the automatic adjustment, the AI planner knows how to reduce the cochlear dose and reduce the beam on time. And also,
can I ask you a question?
What?
Or you prefer to have questions at the end of the
That's fine.
So, thank you. So the dose and the time, right? Are those in your cost function?
Yes.
Okay.
Yes. Yeah, I didn't spend time to talk about my cost function, but that's in my published paper. So I think because the beam on time is a very important criteria for gamma knife, because it can be super long, so we put it into our optimization. Yeah, so it's one of our important criteria. From this table, you can see that this automatic planner could not only reduce the cochlear dose and reduce the beam on time, and also keep all the other important criteria still meeting our institutional criteria. So I use these figures and these tables in my proposal. So to show we have some preliminary result, although it's not for brain mets, but at least we have some experience. So then with all these preliminary results, I submit my first version in October 2020. But at that time, I have a concern that I feel like if the workload of only doing the AI-based priority tuning may not be that enough for our one proposal. So I add another species aim that's about auto brainstem detection, and what we try to bring up some new method. And we already, for that part, I collaborate with my colleague, Dr. Xiaofeng Yang at Emory, and we already published some paper on that. So I added that part as another specific aim. And I submitted it to this study session because I found like most of the reduced surgery related proposal was submitted to this study session. So I submitted to the same study session. And not surprisingly, I didn't get a score, and my proposal was not even discussed. So of course, it took me a while to feel like upset, and I want to give up. I want to stop there. I even doubt that whether this is a good idea, this is a good project for me to do. And then after I finally calm down and I can finally like sit down and open the comments to go through their comments, and I just realized that actually the most comments was criticizing this auto brain mass detection part. Nobody mentioned anything about the auto AI planning part, because I think most of the reviews from that study session were from radiology, not from our side. So they criticized the imaging part a lot. So I think that's my chance. So after 1 year, because I was also preparing for my ABR, so after 1 year, I started revision. The first decision I was made just to remove this brain mass auto detection completely. But that means I also need to expand the specific aim of this auto treatment planning to make it more solid. And then Steve helped me again. At that time, Steve had another R1 get funded. It's still about like AI-based auto planning. So I try to read their abstract and try to figure out what's the new thing they are proposing compared to their first like AI grant. So I steal their idea again and put their idea into my revision of these gamma things. And also, because I want to say that although they already have their AI grant, but their method may not be applicable for my own project. So because that, I just highlight a lot in the revision, the challenge for auto planning for this brain mass projects due to these large geometry variations. So I highlight this a lot in my revision. And then I propose a detailed plan about how to overcome this challenge. Although actually, yeah, I just try to make that plan sounds to be logic, sounds to be workable, but actually I'm not sure whether it'll work or not. And also I add more details for the system validation and at least all the metrics I'm going to use for evaluation. And then I think the most important thing at that time, I study all the study sections. I just read their descriptions and I try to figure out what's the most appropriate one for my application. So then I found this CDM A1, I submitted to this one. And then last but not least, at the last minute, I finally obtained a support letter from Electa to acknowledge the importance and the challenge of my proposed project and show their interest to maybe collaborate in future somehow. So I don't know like which one helps, or maybe I just have a very good luck this time. So finally, I got a very good score for this one. Yeah, so now I just need to work out on this transfer, how to transfer the money from Emory to Chicago. Yeah, so that's my first project. And then the first project and the second project and the second proposal I was working on was about the real-time volumetric imaging for motion management and dose delivery verification for lung SBRT. So I got this idea also from my routine Ph.D. Work. So as Ph.D., I was required to go to the machine to supervise every treatment fraction for SBRT patient. And for lung SBRT at Emory, our motion management strategy is that we will use just 4D CT to evaluate the breathing motion. And if the motion is small enough, we will do free breathing. And we will use cone beam CT for patient positioning. By assuming that the breathing motion during the treatment delivery will be the same as that during the 4D CT scan, and also will be the same as that during the cone beam CT scan. And if we find that the breathing motion is large, we will do gated radiotherapy by assuming that there will be a good correlation between the external surrogates and the internal tumor motion. But I know like a patient breathing will not be always the same, will not be always regular. So although I already proved the treatment, the therapist already started delivery, but just couldn't stop thinking about what if the patient breathing just changed during the delivery? What if patient cough? So what's the actual patient anatomy, and then what's the actual dose delivered to tumor and to OERs? So with that, I started to have some rough idea. I think maybe there's something I can do. At that moment, Dr. Parkhill, and he was proposing a new concept about real-time adaptive radiotherapy. And also there's someone from his group gave a talk in that year's AAPM. They are talking about real-time dose optimized MLC tracking. But all of their proposal on mentioning they are kind of like desire a real-time volumetric image during the delivery. So I feel like, okay, that may be something I can do. So this real-time volumetric imaging, what I mean is that during the delivery, if we keep the KV beam on, if we keep capturing the 2D KV projections during the delivery, and for each 2D projection, if whether I can reconstruct a 3D image at every moment. So actually this is not a new idea at all. So my previous colleague, Dr. Ruijiang Li, he was also Steve's postdoc when we was at UTSW. He actually started this idea and a project along when we was at UTSW. So that's what 10 or 12 years ago. And then he got his K99 when he moved to Stanford for this idea. So he proposed that the main idea, he will build a PCA lung motion model for each patient and use that as the prior knowledge to be able to reconstruct a 3D image from a single 2D projection. But you see, after this already been a while. So after a while, I think people have realized that this long motion model-based method is not that robust enough to be able to handle the variation in patient breathing motion, in patient positioning, and anatomy change. So that's why it's still not being able to use in clinical. So then I'm thinking, okay, so how about deep learning? Whether deep learning can address this robustness issue and to make the real-time volumetric imaging for routine clinical use. So again, I don't have much experience with the deep learning. So what I do is just try to get opinions from experts. So I talked with Xun, and he told me that actually he submitted a proposal of the exactly same idea, but using machine learning, because that's in 2015, and he didn't get it. So right now he has lots of other more interesting stuff he wants to do. So he just stopped trying on this idea, but he still said that it doesn't hurt to give it a try if you want. And then I talk about this idea with my colleague, Dr. Xiaofeng Yang at Emory, and because he's the AI expert, especially in the image side. So he actually liked this idea a lot, and he think it was a try. So that's why we just start to build our collaboration on this project very naturally. So we start to have weekly brainstorming and discussion. And so the first thing we discussed is that how to make it substantially different from that founded K99. So I think maybe one highlight, it should be like we can use deep learning. We can emphasize that we will use deep learning to make it more robust to be able to use for clinical use. And also because Xiaofeng already got a lot of, he's experts in the image segmentation, image processing, and also I have some experience with Monte Carlo simulation, dose calculation, adaptive radiotherapy. So we think, okay, maybe we can move a step forward towards the clinical application of this real-time volumetric imaging to make the proposal stronger. Yeah, so this is what we proposed in our proposal. So first we will propose to achieve AI-based real-time volumetric imaging. And then with that, we will do deep learning-based tumor location to achieve real-time markerless 3D tumor tracking. So it didn't sound that exciting. And then we will do deep learning-based auto segmentation and with my dose calculation, so we can reconstruct actual delivered dose to maybe to do dose-guided adaptive radiotherapy. And also we bring up that with this real-time volumetric imaging on Linux, we can promote the development of the truly 4D radiotherapy and also the real-time adaptive radiotherapy. So that's pretty much what our proposal proposed. So with that idea, so we start our preliminary study. So we build a deep learning model like this to try to generate a 3D image from the 2D KV image. So I think it's blocked here. So we already published a paper about this preliminary study. So if you are interested in the details, you are welcome to just read that paper. But I think the information was kind of blocked here.
So when was that? Which year?
2020.
Was you releasing a paper in Nature BME?
Yes, this paper was after him, and he was just proposed. I think at that time he proposed for the kind of like just one direction, yeah, AP, and he tried all different like a tumor size, and in their per introduction, I think they just proposed for maybe intraoperative procedure or whatever. So we just grabbed that. I think he didn't mention any like long SBRT thing, and then we kind of based on their work, we add like we do this thing. So this one we don't need the projection to be just AP. We can do for whatever arbitrary angle. So it's like just like 360 angles. In order to get the preliminary results, we just decided to, at that moment, we just perform some simulation study. And also, I read a paper from Steve's group about that overfitting thing. So again, I steal his idea again. I think, okay, in order to overcome that large variation to make the model to be more robustic, so we propose that, okay, for this project, we will just train a patient-specific model for each patient. So what we do is that we will generate the training data from patients' own 4D CT images. So in our preliminary simulation study, like we just use like 9 phases of the CT image from the 4D CT to simulate the 2D projection and use the paired like 2D projection and a 3D image for training. And then we will use the remaining phase CT image and its projection as the testing data. So we tested on 20 patients, and we get like a pretty okay result. So you see like this last 2 columns are the image we generated from a single 2D projection. And at that time, we already predict that the reviews may have some concerns about its robustness to handle what if the breathing motion change during delivery from your 4D CT, because we use 4D CT for simulation, and what if the tumor shrinkage at the time of delivery. So we already predict that concerns. So in our preliminary study, we do some simulation. We try to mimic a very challenging scenario that can happen at the time of treatment delivery. So we simulate a tumor motion with doubled amplitude and also with 50% of tumor shrinkage. And we found that, okay, our model is kind of robust to handle this challenge scenario. And we also think that because we will keep the KV beam on during the whole treatment, so definitely the reviewer will have some concern about our imaging dose. So for that, we did some simulation study and try to mimic the 2D projection acquired at low image dose. So we add some image noise to test the robustness of our model, and also we found it did a pretty good job there. So with all these preliminary results with our published paper, so we submit our first version in June 2020. And because we have imaging and also we have dose, so we didn't figure out any good study session for us to submit. So we just submit to RTB. And at the first round, we actually got a pretty good result. We got 21%, but we didn't know why. At that time, we had 4 reviewers, so 2 with pretty good scores and 1 with moderate score, and then the last one with pretty low score. So at that time, if we don't have that 4th reviewer, we will pretty much get it. But yeah, it's just like bad luck. But still, with that result, we were very optimistic at that time. We think if we just persuade maybe the 3rd one improve the score a little bit, and then the 4th one a little bit, maybe we can get it. So because of that, I didn't spend enough time to address their comments for this revision. And also, I think the biggest mistake I made for that one is I tried to argue with the 4th reviewer because I feel like he or she kind of like misunderstood our proposal. So I tried to argue with him. And that's the biggest mistake I had ever made. Then for our revision, I got a score of 49%. We didn't expect that the score can go down that much. And also in the comments, the toughest review insists that he thinks with the MR Linux, so there's no need to develop this real-time volumetric imaging on Linux. So I discussed with Xiaofeng, and we decided to move on. We don't want, so we think that if we stay in this same study session with the same reviewers, we will never get it. Yeah, so we just resubmitted as a new submission to some other more imaging related study session, and then we got a 20-ish percentile again. So I think that's a signal, tell us something that okay, there still something like review like. So at the first round, we can still get this pretty okay score. So I just resubmitted this proposal before our APM. So this time I studied a week, 3 months before the headline. And yeah, we just discuss and read every sentence of the comments. And also I feel like if I have to argue with the reviewer, so this time we found a lot of good reference to support us. It's not just simply argue. We have enough evidence to support our statement. And also we rephrase our statement on impacts and to make sure that all the claimed direct impacts will be validated in our validation study. And we also resign the whole validation study and add more details on the system evaluation. So I think the most important thing is that this time we change our attitude. So we just try to do our best, and then I just cross our finger and leave the rest to God. So after that, I just totally forgot this proposal and work on the next one. Yeah, so for this one, we are still waiting for the result. And then this is the, oh, that's the one. So I think I only have a few minutes. So I will not go into details about the third project, but the idea actually is not new again. We just try to propose to use AI to try to achieve online adaptive proton therapy for head and neck cancers. But what I want to share with you about this is some lessons I have learned from the whole process, because Xiaofeng and I, we have decided that this time we will submit it to NIBIB just because they have much higher pay line. So we submitted it to NIBIB, and the tricks we did is like we didn't mention the cancer type in abstract. So we try to make it like more general, like sounds like a platform. So with that tricks, we successfully get into NIBIB and we got a score of 26%. So that's very close to their pay line. So we are very excited, and we work on the resubmission and submitted this year, March this year. So we got a score of 14%. That's within the pay line of NIBIB. And we were very excited until we paid attention to the detail that this time, we don't know why, but it was assigned to NCI instead of NIBIB. So that means we didn't get it. So we tried to contact the NIBIB director, I tried to contact the NCI director to see what happened, and figure out that at that time, the NIB director, he heard from someone that proton is for cancer treatment. So he think it may need to go to NCI. So he organized a meeting with all the experts, and what they do actually is pretty simple. They do research. They try to find the high frequency words in our proposal, and they found the two high frequency words, AI and cancer. And then because cancer, our grant was pushed to NCI at resubmission. So we try to communicate with him to see, we already know that we cannot get it back to NIBIB now, but we try to see what's their criteria. Maybe next time we will pay attention. And he said, if you mention tumor, then it may be okay for NIBIB. But if you mention cancer, it will have a bigger chance to go to NCI. So that's the very expensive lesson we have learned from this process. So that's what I want to share with you guys about the lesson we have learned. Yeah, I think that's pretty much what I want to talk about today. And yeah, thank you for your time and attention.
This is a wonderful talk, very valuable lessons.
Yeah, you see, I share all my secrets. The last two are not funny. It's all our secrets.
Yeah, especially for useful for future faculty and residents, right? We work on our way in the future. Lots of useful. Yeah. So questions for them? Anyone?
Yeah, I always think like this is very useful. I think like for many lessons, I think like that basically probably starting to propose every side. I think many lessons I think also kind of probably share in my early stage. But I will ask kind of probably technical questions. So now with gamma knife, right, we have that lightning. So our physician like a lot. I think other that probably single shot for small mates, they always use lightning, and just a few clicks they will get the plan. I'm just curious whether you have plan to sort of like compare whatever you propose with this direct motion solution lightning.
Yeah, so like last year, I think the lightning was came out last year. Yeah, so I was almost giving up. It's not a good timing, but I think, okay, maybe I will just give a last try. If I will not get it, maybe I will modify this proposal for like maybe Linux-based multi-meds stuff. So that's my plan. So that's why I submitted this proposal. I didn't have any hope to get it, and then I moved to Chicago, and Chicago doesn't have gamma knife. That's the whole story. Yeah, so, but just because of good luck, I had that. So yeah, definitely I will compare with their lightning, and also I discussed with my colleagues. So Lightning is still like inverse planning. So I can still use them and based on their new platform to do this like AI-based things.
Yes.
Yeah,
You
still
use some like parameters.
yeah, so you still need to choose priority things, but you still don't know like which priority work best. You still need to have maybe multiple plans for physician to choose. Yeah, so I think there are still something I can do, maybe not that much, but yeah.
So which part of the grant process did you find most challenging?
Which part?
Yeah, was it the writing part or the waiting part?
No, I think maybe it's the beginning. I think the most difficult part is actually try to find a good like problem to solve. Yeah, so I think so. See, that's the very different from the project we do when we were student or postdoc, because our supervisor just give us the project. We don't need to find a project. They give us project. We just need to figure out what method to use. But right now, if you want to be an independent research, then you have to think from the very beginning. You have tried to find a project and people haven't done that, and it's still like maybe have enough significance. So yeah, I think the most important is actually at the beginning. Once you figure out the problem, then yeah, you can take step by step to do that.
I think I agree with Zhen. That's the most important part. On the good clinical problem that is significant, urgent, right? That can make a big impact there. That's the most important part. But to get there, I think you have to have a clinical experience for working in the clinical environment. So you understand, you interact with the clinicians, right? But you know, kind of information. And I just sit in your office imagining what's important, right? That will be challenging, right?
Yeah, so you see, all the first two projects I actually got the idea from my routine clinical work. And because I have the feeling, then I start to think about it. If I didn't work on that, I will never think about what to improve.
Yeah, just sort of a follow-up question to that. Like, how often would you say like you've had an idea and it didn't even get to the preliminary study? Like, what's the ratio of like ideas that just didn't work versus the ones you actually try to go to?
Right now, for me, maybe half and half. Yeah.
That's better than I thought it would be. But thanks.
And I think the good thing that if you find the problem and you can try to justify, as long as you can try to find so for the first galvanized things, I already saw Xue R1 and it sounds to be very familiar. So if I stop there, I will stop there. So, but I just decided to try to find whether like what they are proposed are different from mine, whether I can sell the story from another point of view. Yeah, so you can try to justify that.
Yes, hi, Zhen. This is fantastic.
You missed my whole talk.
No, I didn't. No, I was listening. I was listening to half, and when you started again, then I started coming here. So
Okay.
I have a question about that. I want to congratulate you first because you probably did it in 2 or 3 years. What like that took like 10 years to develop. So that's fantastic and impressive. But the second question is, in the meanwhile, they released this new optimization.
Jing already asked me that question.
Oh, then I'll talk to you later. Sorry.
For the first project, you said you get a support letter from Electa.
Mhm.
So how much do you think that helps? Like,
I
is
don't.
it like a real collaboration or?
No, it's not real collaboration. I just try to get a support letter, but I don't know how much it helps. But I think it definitely helped a little bit. From their industry said, oh, this is a very challenging problem. If you can address that, we can collaborate. So I think they definitely play some role there.
So sometimes you don't know exactly how much it's going to help, but you know it will help. So you try your best to get everything may help there, right? Thanks. More questions for today? Any questions online? Ricardo, do you see any online?
No questions online.
Okay. Well, if not, let's thank them again for one more time. So the reasons if you guys have had, you want to stay here, how to join, about having